Tell me.
Ink have a smell.
They have a smell. Very good. Okay. So the one thing is there, which is smell. So you will be only knowing about this smell that is present there. You will not be knowing about this ink pot, and neither you will be knowing about this pen. Right? Yes or no? If your eyes are closed, correct? Okay.
Yes.
But what you may also feel is that you may also feel this ink as it may travel to your hands, right? When ink has been spilled, it can flow and it can travel to your hand, and then you can have, okay, fine, there is something liquidy here, there is something which is present, and if you can smell it, then it is, you'll say that, okay, fine, it is ink. Now there are three types of thing, as you can see here. There are three types of thing, as you can see here. There are a few things. In order to know their presence, you have to touch them, and that means you have to do some movement, and you can only know by touching them if your eyes are closed. I'm just thinking in terms of eyes are closed. And there are a few things that can travel to you, and you don't have to travel. For example, this ink, you don't have to travel to ink. They can travel, and then you can touch it, and then you can feel it. Now there is smell. There are some particles of this ink which is in the atmosphere around you, the surrounding around you, that is not even requiring your movement at all, and like they will obviously reach your nose. So here in ink we have a possibility that it may or may not reach your hand, but smell, it will surely reach your nose, right? Smell will surely reach your nose. Now you have three things, right? Now there are a few things which do not move at all. There is something which move a bit, and there is something which moves a lot, right? And by this classification, we can classify, by this basis, we can classify things into solid, liquid, and gases. So you can imagine that if in very ancient time, when we did not have this idea of solid, liquid, and gas as a classification, then this type of situation or an event could have happened. For example, Apple was hit, right? Apple was hit on the head of Isaac Newton, as the story goes, and that was the event that inspired him for the discovery of gravitation and working on gravitation. Now this kind of situation can also happen, and some scientists can infer these things and classify things into solid, liquid, and gases. Okay. Now one of the main focus of science, if you see this word science, and there is another word which is scissors. Both of them have this SCI, and both of the roots are similar. Their roots are similar. The root word for science and scissors are similar. And what is scissors used for? Tell me. Cutting, right? And one of the very important work of science is to cut things, and that means we have to classify things. Okay, that means classify things. So here you can see that's one of the main work of science is what? It is to classify things. Okay. Then let us classify the solid. First of all, we will define the solid, then we will classify the solid. And when we are going to define this solid, we are going to define the most fundamental definition. Okay. And can somebody define a solid to me, like right now, whatever definition you know of?
It has height, length, and a breadth.
Sorry?
Height, length, and breadth.
Height, length, and breadth. Okay. Okay. So you're talking in terms of mathematical solid, by the way. Okay.
Oh, okay.
So in
chemistry,
you're talking in terms of mathematics. In mathematics, we have dimensions, and we define things in terms of dimensions. So you have a point.
Its molecules are closely bonded.
Then you have a plane, point, plane, and then you have solid. So this is 0D. This is 1. Sorry, you have point, then you have line. This is 1D, and plane is 2D, and then solid, which has a length, breadth, and height, that is 3D. Okay, so that is in terms of mathematics and geometry. But in terms of solid, so in terms of chemistry and science, Boyle.
Sir, the molecules are closely bonded.
The molecules are closely bonded. That is the most fundamental definition. Now, molecules are closely bonded. That means there are two molecules. We have in H2O, if we see H2O, then in H2O, that is a solid. That means ice. We are not talking about these bonds. Please remember that. When we talk about solid state, we are not talking about the bonds that is present between the molecules. We are talking about an interaction that is present, between the molecules, not inside the molecules. So we have one water molecule here, and we have another water molecule here. Okay, so the interaction between these two water molecules, right, that will lead to a solid state, and this interaction will be high. The intermolecular forces of attraction will be strong. This is the fundamental definition. That is, intermolecular forces are strong relative to the liquid and gases. Now, what will be the consequence of intermolecular forces are strong? If intermolecular forces are strong, the molecules or the molecules that is making a solid, they will be very close together, and their distance, that means intermolecular distance, will be very short. Correct. This is now consequence of a strong force. Now, when the intermolecular distance is very short, they don't have a very large area to travel, and hence what they do, they oscillate on their mean position. The molecules, they will oscillate. Now, this is the another consequence. Okay, the constant particles, they will have fixed positions and can only oscillate about their mean positions. Now, if you cannot have, if they don't move at all, they will not even move even if you apply some pressure. Right, and that is why these are incompressible. That means even if you apply some pressure, they are not going to get compressed, and that is why they are rigid. And after this, we have the last statement, which is the consequence of all of these four, and that is a definition that you must have heard, learned, read in lower standards. So that is, they have definite mass, volume, and shape, and shape is the most important thing in solid, because for example, liquid, it has mass and volume, but it does not have a definite shape, because if you have 1 liter of water in a bottle, it will look something different. If you have 1 liter of water in a jug or a jar, it will look something different. Okay, so I hope you understand that intermolecular forces are strong. The consequence is that the intermolecular distances are short, and further on, they don't move, and they have fixed positions. They are incompressible, and they have definite mass, volume, and shape. Is this clear? Yes or no? Please tell me.
Yes, sir.
Yes, sir.
Okay. So moving on, after the basic definitions and characteristic properties of solid state, let us now classify the solid state. Okay, let's now classify the solid state. So the solids, they are classified into two types. So we have seen that a solid can have a very long range order, okay, on the basis of order. That means if I start seeing an atom here, then I saw there is same type of atom present. When I say same type of atom present, it doesn't mean that it have to be same only. You will have a red atom here, and then you can have let us suppose a yellow atom here. Okay. Let me change the color. A red atom here, and let us suppose you have a blue atom here. Okay. So it means, and after that also you have a red atom here. Then you have a blue atom again. Okay. Now, this may give us some predictability that if I go on moving, I can see the first atom is red, second atom is blue, so first atom is red, second atom is blue, right? So you can see that the odd places are captured by the red, and it means that if I go to the, let us say 91 atom, it is going to be red. So there is a kind of order and a pattern in this type of solid. But there are other solids which are not very pattern wise. So you have atoms like this, and then the atoms may deviate and they may have some imperfections like this. Okay. So there are these type of solids, right? Now in this type of solid, we can't predict anything. And as you can see, this have a long range order, and they have some order, but those order are short range. Okay. So these are also ordered, you can say, but these are short range orders. Okay. There are orders in here, but these are short range. So the solids are classified into two types on the basis of their nature of order, that is crystalline and amorphous. We have crystalline solids and we have amorphous solid. Okay, so crystalline are the one which have long range order, and amorphous are the ones which have short range order. Okay, Acha. So whatever text you see in this whole slide, these are only because I will send you the PDF and then you will copy it down. Okay, so everything what is present in the text, I have already explained it, as you can see. That is on the basis of the nature of order present in the arrangement of constituent particles. So crystalline have long range and amorphous, they have short range order. Now you guys tell me, what do you think? The picture A is crystalline or amorphous?
Crystalline.
Crystalline. And B is amorphous, right?
Yes,
It is very much clear. So both of them are of same molecule, as you can see, red and blue, and it is both of them are SiO2, but due to the virtue of their like making how they have been made, so this is a crystalline SiO2 and it is known as quartz. It is known as quartz. So it is crystalline and hence it is also known as quartz, that is crystal. Okay, and it is a short range order and it is known as quartz, which is glass. Now, when you hear this term glass, please remember that it is not mirror. In solid state chemistry, glass, it doesn't mean mirror or mirror type of thing, or even it will be, it doesn't mean that a glass will be, let us say, transparent also. Okay, it doesn't mean that the glass will be transparent. Glass means any solid that has a short range order, it is known as glass. Okay, if you have a solid that has a long range order, it is known as crystal. And if you have a solid which has a short range order, that is known as the glass in solid state chemistry. In solid state chemistry, glass is known as solid which have short range order. Will you be able to remember this? Yes or no? Please tell me.
Yes, sir.
Okay. Now moving on to further more differences between crystalline and amorphous. The first fundamental difference, and this is the most fundamental difference. Okay, and this is the difference due to which the other properties, they are differing. So the whatever you see later on, these are the consequences of this long range order and short range order. So if you have long range order, then it means it will give out and give it you a geometrical shape, right? A definite geometrical shape will be given out if you have a long range order. But for amorphous, there will be irregular shape. There will be some irregular shape. If you have a very characteristic geometrical shape and you have a long range order, then the solids, they will melt at sharp and characteristic temperature. For example, if I take water that is from, let us say, India or from the kingdom, both will have a melting point of 0 degrees Celsius, right? The ice will have a melting point of 0 degrees Celsius. So it is very sharp. That means you have a one perfect temperature and it is characteristic temperature for water. Now that will not change if you're going to take some other ice from some other continent. Okay, so they melt at a very sharp and characteristic temperature. But this amorphous solids, if you have ever melted and tried to heat a plastic, if you ever try to heat plastic, have you ever seen a liquid plastic? Have you ever seen a liquid plastic when you heat it?
No, sir.
No, na? Even like you may say that nahi sir, wo jal jata hai na? It gets burnt out. So I'm not asking you to burn it or directly throw it in fire, but I'm just asking you to heat it. For example, how you can heat? You can see how the plastic gets heated when you have a very hot utensil and you just touch a plastic onto it. Then what will happen? It will get soft, right? So what happens with amorphous solids? They get soft over a range of temperature. Okay, they don't have a very characteristic melting point, and since they don't have any characteristic melting point, they don't have a definite enthalpy of fusion also. Fusion is the energy required to go from solid to liquid, and since they don't have any characteristic temperature at which they melt, that is why they don't have definite enthalpy of fusion. Whereas crystalline solid, they have definite and characteristic enthalpy of fusion because they melt at a sharp temperature. Now, next is if you have crystalline solid, then when you cut the crystalline solid, then what is going to happen? When you cut the crystalline solid, they will be having very smooth and plain surfaces, right? So if you have a solid and you cut it in two parts, then what is going to happen? You are going to get this as a new surface and this will be as a new surface, right? So both of these surfaces, they will be very plain and very smooth. Again, why? Because there is a long range order present. There's a long range order present. If you cut here, the atoms will be like this in both the cases, right? Because we have long range order. But if I cut amorphous solid, then you may imagine that let us suppose we have a solid amorphous which is like this, and it is having randomly arranged atoms. Let us suppose if I cut like this, so you can see that in this surface I have only 2 atoms, but in this surface we have 3 atoms. So obviously the density will be higher here and it will be having some kind of ruggedness, and there will be some irregular surfaces when we cut amorphous solid into 2 pieces. Okay, now crystalline solids are true solids, but amorphous solids are known as pseudo solids, or these are also known as supercooled liquids. These are also known as supercooled liquids. Now, the next property that is there, that is anisotropic in nature and isotropic in nature, that I will explain in the next slide. Okay, what does this mean? Anisotropy and isotropy. So crystalline solids are anisotropic in nature and amorphous are isotropic in nature. What is that? We'll look at it. Examples are, wait a second. Okay. So the examples for crystallines are NaCl, ice, quartz, and diamond. Again, this quartz, the crystal quartz, and amorphous, you have glass, rubber, and plastics. Okay, glass, rubber, and plastic. So before going on to anisotropic and isotropic, we will look at a quick example on how to classify the solids. So you have this question in which you have to classify the following as amorphous or crystalline. Amorphous or crystalline. Okay, so amorphous are all the plastics. They are all amorphous. Okay, so plastic, it is what? Polyethylene. So anything that has that is a polymer, that is going to be in the classification of amorphous solid. So you have polyurethane, which will be amorphous. You have naphthalene. Now naphthalene is not a polymer, it is a compound, and similar to water is also a compound. Naphthalene is also a compound, right? Now if you have a lot of naphthalene, those naphthalene balls, these are crystalline. So this will be crystalline. Similarly, benzoic acid will also be crystalline. Teflon, it is just like polymer, which will be amorphous. Potassium nitrate is now an ionic solid, just as sodium chloride, right? Magnesium chloride, potassium nitrate, right? Lithium nitrate. So this also will be crystalline solid. Cellophane is again a amorphous because it is plastic. Those things that you wrap your gifts with. Polyvinyl chloride. So these are like PVC pipe. Polyvinyl chloride, PVC. So PVC pipes are also kind of plastic, and these are amorphous. Fiberglass, by the name suggests it is glass, it is amorphous, and copper, it will be a crystalline solid because it is a metal. So generally speaking, if you have something such which is a molecule, or it is a metal, or it is ionic in nature, then all of these will come under the umbrella of crystalline solid. Okay, crystalline solid. And these are the names that you must have heard already. For example, polyurethane, you haven't heard, right? Teflon, not in the context of chemistry, maybe Teflon pans you may have heard. Similarly, cellophane, polyvinyl chloride, fiberglass, these are not compounds. You can easily see that. These are not compounds, rather these are polymers. You can see all the polymers, they are going to be amorphous. And the names that you haven't heard till now, you can safely put them in the bracket of amorphous solids. Okay, if you don't know. But first of all, try to look at the crystalline, whether it is crystalline or not. If it is not crystalline, then put it in amorphous. Okay, so this is the classification. Next is, so what is going to happen? Here I have written the answer, but in crystalline solid, I missed one thing, that is naphthalene here. Okay, so you may have to add that. I missed naphthalene like completely from this answer. So in amorphous also, I have not put the naphthalene because it is not amorphous. And I forgot to put the naphthalene in crystalline. You may have to add naphthalene in the answer. Okay. Now moving on to the anisotropic nature and isotropic nature. Now, in crystalline and amorphous solids, when we measure any property, we are going to measure a property. Okay. We are going to measure a property. Now, the property can be measured in two different directions. We can measure it in this horizontal direction, and we can also measure it in this vertical direction. Okay. Now, properties of a solid or any compound are due to its atoms. Is that right? Yes or no?
Yes, sir.
Okay. That means if I am measuring, then the number of atoms I come across while measuring any quantity is going to affect the value of measurement, right? Yes or no?
Yes, sir.
You can imagine if you have thin glass and if you have a thick glass, and the light is passing, then what is going to happen? Right. So if you have a large number of atoms that is coming across, then that will that will change the value if you have relative to the value that you get if you have lower number of atoms. So if I look at this horizontal direction that you can label as X, I have 1, 2, 3, 4, 5, 6, and 7 atoms which it is crossing. But if I look at the Y direction, it has 1 complete atom, 2nd complete atom, 3rd complete atom, and 4 complete atoms, right? Yes or no? Can you see that?
Yes, sir.
Right. So in crystalline solid, what happened? In crystalline solid, the physical properties give different values in different direction. Okay, in different direction, because the number of atoms that we are coming across, it is going to be different. The number of atoms that we are coming across is going to be different in different directions. And as you can see, this is crystalline, right? This is crystalline. Now in amorphous, if I look at amorphous, then let me also make two lines like this. And let us count 1, 2, 3, 4, 5, and 6. And here we have 1, 2, 3, 4, and 5. Now, as you can see here, also we are having a bit of difference, that we have 5 atoms here, we have 6 atoms here, but the difference is not very large. The difference is not very large, as was the case in crystalline. Now here, the range of values that we get, it is very large, but in amorphous also we get slightly different values in different direction, but essentially the range is not very high. The range is not very large, and we say that in amorphous solids, the properties are same. The value of properties are same in different direction. Okay, in different direction. That means the value of properties, or the magnitude of properties that we are going to measure, it does not depend on the direction in amorphous solid. That is why it is isotropic in nature. And in crystalline solid, they differ, and that is why it is anisotropic in nature. Okay, that is why it is anisotropic in nature. Okay. Further moving on. Now, in this slide, again, I have shown that if you measure in this direction, you will get only blue atoms, but if you measure in this direction, you will get blue and orange atom both. That is why the magnitude, or the whatever value you are getting for a physical property, that is going to be different. Achha, now these are the things that you will write, that we have already explained about crystalline solid, and here we have about the amorphous solids. Okay, fine. So you understood about these two words, anisotropic and isotropic? Yes or no? Tell me.
Yes, sir.
All of you?
Sir.
Anna? So first thing is the definition. What is isotropic? Anna, what is isotropic? What is isotropic? So you will say same value of physical properties in different directions. Okay, different directions. And what is anisotropy? Anisotropy is different values in different direction. Okay, so one thing is that you have to understand the definition of anisotropic and isotropic. Then you have to understand the cause. Okay, and generally speaking, you will be asked about the cause of anisotropic. What is the cause of anisotropy in crystalline solid? So you have to remember the cause also for anisotropy. Okay, so moving on. Now we have classified solids into crystallines and amorphous. And in crystalline solid, we saw that there is a long range order we can have, and we can do some kind of predictions. But if I look at the amorphous solids, these are not long range, these are short ranged, and I cannot do any efficient predictions if I look at the amorphous solids. Yes or no? So here we can't do any prediction. That is why initially what happens, we start with the things which are simple and which are nice and very elegant. That is the crystalline solid. So in this class, you will be only learning about crystalline solid. There is no other detail about amorphous solid required. Okay, so whatever you have learned till now, that is all about the amorphous solid. Now we are going to classify again the crystalline solid on the basis of intermolecular forces of attraction. Okay, on the basis of intermolecular forces of attraction. So the first classification, the first type of crystalline solid is molecular solid. Now in this molecular solid, now with all of these classification, you will remember two things. You will remember first of the things is constituent particles. Constituent particle. And then the next thing that you are going to remember is the IMF between constituent particle. IMF between the constituent particles. Okay, intermolecular forces of attraction between constituent particles. Now listen very carefully. You can have a solid nitrogen, right? You can have solid N2. Now in solid nitrogen, what is the intermolecular forces of attraction? Now someone who is learning solid state for the first time, they will say, sir, triple bond hota hai sir nitrogen mein, right? And now what you will see? You will see the force of attraction, that is a triple bond. Yes or no?
Yes, sir.
But is that the case? Is N2, the solid N2, is the intermolecular force of attraction in N2, is it triple bond? No. The triple bond is the force of attraction between two atoms of nitrogen. Whenever we are talking about solid state, whenever we are talking about different phases, we are talking about different molecule as a whole. So we have two N2 molecules, and we have millions of N2 molecules, and they should be connected, or they should be having some attractive forces of attraction between them that is making them stick together like a solid, that is making them stick together like a solid. So this type of interaction, it will be what? It will be obviously non-polar, right? It will be non-polar, right? And in non-polar, because N2 and N2, these are non-polar, and if it is non-polar, that means this molecular force of attraction will be dispersion force, or if you remember the states of matter, it is London forces. Do you know what states of matter 11th class से हटा दिया गया? Do you know that?
No, sir.
The states of matter has been removed, and they also removed something else. Yeah, they removed the complete S block, P block from 11th standard. Fair. So we have dispersion forces and London forces in non-polar solids. Okay. Similarly, N2. Similarly, you will have argon gas. Argon gas is also going to be non-polar because it is a noble gas. Similarly, I2H2. So all the non-polar molecules, if you solidify it, they will be having dispersion or London forces of attraction. They will be non-polar molecular solids, or you can classify them as molecular solid in general. For polar, you can have HCl, right? If I have HCl and I solidify it, oops, sorry. Okay, no problem. Just look, if you have HCl, so we can have a dipole moment like this. H plus will have a delta positive, Cl negative have delta negative. Similarly, again, another HCl, delta positive, delta negative, right? So you can have dipole like this. There will be interaction between this delta positive and delta negative, and this interaction will be what? Dipole interaction. So polar molecule have dipole. Similarly, if you look at water molecules, so water is H2O. So between one water molecule and the other water molecule, there will be a force of attraction that is known as hydrogen bonding. Yes or no? I hope you guys remember it.
Yes, sir.
Hydrogen bonding. So this is all about the molecular solid. The constituent particles in all of them you can see is what I2 is a molecule, H2 is a molecule, right? HCl is a molecule, SO2 is a molecule, ice is a molecule, right? Even if you say argon is a molecule, yes, argon is also a molecule. Okay, argon is also a molecule. The molecule is anything that if you can take something in your hand, that is going to be a molecule. Okay, now recently I've been come across some scientists in chemistry. They are now going to define molecule in a very specific way. Okay, very specific way. Let us see. In a few days, I was seeing some of the papers. They are going to define molecules once again. Let us see what they come up with. Okay, after molecular solids, we have now, you know what? Chemistry is one of those subjects in which things are always changing. And that is why you can understand that it is one of the most, what I can say, recent sciences. Like for example, maths, it has been sold that nothing changes in maths. Okay, at least in this level what you're understanding. Obviously there are daily improvement, and there are daily some new theories in mathematics and some improvement in the subject. But in chemistry, physics, biology, then if I talk about chemistry, physics and biology, then the most is there in like in your terms it is there in chemistry. But if I look at the as whole, biology is one of the most research subject, but chemistry in your level, you can understand what were the changes happening. Okay, fine. Next is the ionic solid. In ionic solid, we will have the constant particles as positive and negative ions. Now, if I look at NaCl and we have Na plus and Cl negative, now what is the force of attraction between them? There is Coulombic force of attraction or electrostatic force of attraction, right? So you must be learning about Coulombic force of attraction in 12th standard. Electrostatic chapter. Electrostats is a chapter, right? Electrostatics. Electrostats. Yes or no? नहीं. Class नहीं start हुई आप लोगों की physics के? Yes, Ishan, Hamza.
Yes, we completed.
You completed, na? So these are the electrostatic force of attraction or Coulombic force of attraction in ionic solid. Okay. Now moving on to the metallic solid. Now in metallic solid, let me give you guys how a metal is there and what is the type of, what is this metallic bond that is present. So positive ions in sea of electrons. Okay, so positive ions are the constituent particles. So if I have sodium, so sodium, it will exist as the sodium metal will have Na plus, okay, and its electron will be somewhere away. Okay, then you will have another Na positive, its electron will be somewhere away. Then you have another Na positive, its electron will be somewhere away. Okay, now obviously these all electrons are moving here and there. Okay, these are all moving here and there. Now, this electron, if you look at this sodium atom and the sodium atom, both of these are having positive charges. Now, essentially, they should repel each other and they should go as far as possible. But the electron that is present in between, so this electron is attracted by this sodium atom. This electron is also attracted by this sodium atom. And that is why this electron is the one that is making a bridge between these two sodium cations, and it is keeping them together. It is keeping them together. So this type of bonding, it is known as metallic bonding. Okay, this type of bonding is known as metallic bonding, and these are present in the general metals you see: copper, silver, iron, Mg, gold, and all of them, they will have metallic bonding. The important thing is that the constant particles are the positive ions, okay, positive ions. Now the next one is the most important, that is covalent. That is covalent or network solids. In covalent and network solids, have the constant particle as atoms. If you look at diamond, so diamond has this type of structure in which all the four bonded atoms are carbon. Right, all the four bonded atoms are carbon. All the four bonded atoms are carbon like this. Okay, so what you can see here, that this whole branching, it will just continue. If you look at the atoms here, which is constant particles, the constant particle here is this one carbon, let us suppose, and this another carbon, let us suppose. Okay, and what is the force of attraction between them? The force of attraction between them is a covalent bond. Okay, so this is the only one in which you can write covalent bond as the intermolecular forces of attraction, because the atoms that is making a covalent or network solid, it is having a intermolecular force of attraction, that is a covalent bond. Okay, between these two atoms we have covalent bond. But please remember, if you have water molecules, then water molecules, they have hydrogen bonding. Okay, they have hydrogen bonding, so their structure is not like this network. It is one molecule of water is connected to another molecule of water via hydrogen bond. But in covalent or network solid, each carbon atom is connected through a covalent bond. So is this classification clear about molecular, ionic, metallic, and covalent or network solids? Yes or no, please tell me.
Yes, sir.
Okay, now please write this question. Let me know when you're done writing the question.
Done, sir.
Okay, so potassium sulfate, what type of solid will it be on the basis of intermolecular forces of attraction. Will it be molecular, ionic, covalent, or metallic? Potassium sulfate.
Ionic.
Ionic, correct. Very good, ionic. What about tin?
Metallic.
Metallic, correct. What about benzene? Benzene is the molecule as water is a molecule, right? So it will be molecular solid. Similarly, urea, again, molecular solid, ammonia, water, all of them will be molecular solid. What about zinc sulfide?
Ionic.
Ionic. Okay, graphite,
Covalent.
covalent, very good. Rubidium,
Lithium is ionic, no molecular.
metallic, na? It is an
Metallic.
atom metal. It is a metal, okay? Okay. Argon,
So rubidium
Molecular.
sorry. Hamza, what?
is a metal.
I could not hear you. What are you saying? Hello?
If rubidium is a metal.
Oh, get your mic fixed. I don't know. Can anyone hear what Hamza is saying? I could not hear it.
Sir, I think he's asking if rubidium is a metal.
Ah, rubidium is a metal. Yes, yes, Hamza. Rubidium is a metal. Okay. Fine. Next is argon. Argon will be molecular. Silicon carbide will be a metallic, sorry, covalent solid. Okay. Now, please remember, if you have silicon, sorry, silicon generally it will have a covalent type of structure. One thing that you should remember is you have silicon dioxide, SiO2, and you have carbon dioxide. Okay. Silicon dioxide, it is covalent or covalent solid or network solid. CO2 is going to be a molecular solid. Okay. Now you will also see this in p block elements. Okay, in p block. So do we have p block this time? I don't know. I haven't checked properly. So in p block elements, you will learn why does SiO2 and carbon CO2, since both of them are in the same group, but still this is a covalent solid. This is a molecular solid. And also you'll understand why SiO2 has only single bond, whereas carbon, it has pi bond also. Okay, so the SiO2 only makes sigma bond, but carbon dioxide, it has pi bonds also. Okay, so you will understand this phenomena, and you will look at various other different elements which are after the third period. They tend to not make pi bonds, they make sigma bonds, and rather than making pi bonds, what they do, they have network solid, or they are hypervalent. So they will make more than 4 pi bonds. That means they will be hypervalent, but they will not be making pi bonds. Okay, so you'll understand this in the chapter that is p block. Okay, moving on. Now this classification is done. Okay, the classification part is done. Now let us move on to the crystal lattices or crystal structures, crystal systems that we can have in a solid. So if you look at this whole plane that is present, you can imagine that this is wall. And if I ask you to fill this whole wall with tiles, right? So what shapes of tiles can you make? You can have rectangular tiles, right? As it is the very normal case. You can also have a square one, yes or no? You can
Yes.
also have a square one. Similarly, now please remember that I am not restricting you. I am not restricting you to a particular shape of the wall. Okay? Particular shape of the wall. What you just need to do is, if you have rectangular tiles and you are just keep on adding rectangular tiles, right, in all the direction, then I just need it to be, I just need it to not have any vacant space between the units, between these tiles. Okay, there should not be any vacant space between these tiles. And similarly, what you can do, you can also have triangle. You can also have triangle. You can have triangular tiles, and then you can just keep on adding triangular tiles. And what you will see is that you can occupy a space that is in the shape of a triangles. with triangular tiles also. Yes or no? Can you see that happening?
Yes, sir.
Anna. Now you can also do this in the, with parallelogram. Yes or no? There is no vacant space left. Correct?
Yes, sir.
Okay. But I want you to look at this triangle and parallelogram. If I look at this triangle, then I can see that, oh wait, we have a parallelogram here. Yes or no? Can all of you see?
Yes, sir.
And not even parallelogram, not even just parallelogram, we also have a hexagon here. So even if I have hexagon, so hexagon maybe if you have hexagon like this, okay, so I can keep on making, and all of this are same only. Either you have triangular or you have parallelogram or you have hexagon, they are almost same. And you can see that in triangle you can get hexagon and parallelogram both, and in triangle you can get parallelogram and hexagon, both of them. Now let us understand what are the different types of this is in 2D, right? These are the different shapes with which we can fill a 2D structure. But if I look at pentagon, if I look at pentagon, and you can see that I have tried to make pentagon and I have tried to make copy it on all the direction, but what I am getting vacant spaces. Yes or no? Can you see that?
Yes, sir.
So if you are ever a civil engineer or interior designer, whatever you want to be, never get pentagon shape of tiles. Okay, ऐसा मत आइडिया दे दीजिएगा किसी क्लाइंट को अपने कि पेंटागन टाइल्स लगाते हैं आपके घर में, है ना? पेंटागन के बाद फिर आपको you will also have to make some purchase of parallelogram or kite shape of tiles, right? So you can have pentagon tiles, but you also need some parallelogram, or you can say it is kite type of shape that you have to put. So now there are only a few ways in which we can fill space, right? As you can see, pentagon is not able to fill the whole space. There are a few things that can fill space, right? Fill space in 2D. Now we can do the same thing in 3D also, and this was what many scientists they tried and they thought about it. Let us now look at those names first of all. Who were those scientists? So the first name comes in this field of study is of Robert Hooke. Acha. Do you know Robert Hooke? Have you come across this name?
Yeah,
Who is he?
he's a chemist.
Sorry?
He's a chemist.
He's a chemist. Actually, he's not. But Robert Hooke, where did you hear about him? In chemistry. Chemistry में कहाँ पढ़ा है आपने Robert Hooke? नहीं पढ़ा आपने Robert Hooke.
In school, sir.
Sorry? Hamza?
In school.
What did he say, Mariam? Hamza ने क्या कहा?
In school.
अरे in chemistry, which chapter I am asking? Robert Hooke. Where will you learn Robert Hooke in chemistry? In school.
One chapter was there.
One chapter was there. No, Robert Hooke's not there. Okay. Yeah, I think yes, Aisha, you're right. But you have learned about Robert Hooke in physics last year.
Yes, sir.
What is that?
Something.
Hooke's law. Correct. You have learned Hooke's law. So he's the same Robert Hooke. And do you remember Robert Boyle?
Yes, sir.
Yes, sir.
And Robert Boyle, you may remember from the Boyle's law. And Robert Hooke was student of Robert Boyle. Okay, so was student of Robert Boyle, even though he was not, he does not have very much contribution in chemistry, but he has contributions in physics most of the times. So, but Robert Boyle used his, he was very good experimentalist, and he used to make very good, what I can say, instruments. Yeah, he was very good instrumentalist. He used to make instruments for Robert Boyle, and Robert Hooke was one of his students while he was performing, and while he gave the Boyle's law. So for Boyle's law, whatever instrument was used, it was made by Robert Hooke only. And both of these are English scientists. And if you look at this year, that is 1660, What was happening in 1660? What was the state of English Empire, the British Empire in 1660? Tell me. Hmm?
I don't know.
I don't know.
Uh,
Arre, bhai
Silver.
saab. What did he say? मेरी को आवाज नहीं आ रही सही से. मरियम, आपने सुना? किसी ने सुना? आयशा?
No, sir.
No. Okay. Ishan, you also did not hear what he said. What was happening in 1660?
Sir, the restoration of monarchy outside civil war.
Civil war. नहीं नहीं, हम in terms of British Empire I'm talking about. Talking in terms of British Empire. ज़्यादा भी आ रहे हैं.
Sir, in 1660, the monarchy of the British Empire was restored.
Monarchy. He is giving such specific dates. In 1660, monarchy of the British Empire was restored.
So I remember
Since-
Charles King from that time.
Yeah, but okay. But you may also remember that they were colonizing the whole world at this time, right? Hannah? Yes or no?
Yeah.
So they were always colonizing, no?
Not no, how they can always colonize. If you remember, like the peak of colonization was in 1660s. I think Jahangir would be the empire of India, right? Huh? No.
Sir, I think the peak of British Empire was during 19th century. 18.
Sorry, Ihsan. Sorry, Ishan, what?
Peak of British Empire was around 18th and 19th century.
Yeah, peak of they were starting to colonize things, right? If you remember, in 1660s, around 16, this was after Jahangir, I think. So Jahangir was the one who welcomed the East India Company. Okay, so during Jahangir's time, East India Company, it was as a company at that time. East India Company was there, but please remember, East India Company was not just a company. They had their own military and all, right? It was the most powerful companies of all time. It has its own military. It used to conquer things. Now, obviously, it had the backing of British Empire, but it was still a company. It was a government company, you can say. Still, it was a company. Okay, so at 1660, British was trying to colonize the whole world. They were going every place, and for that they needed military, and they also needed artillery. And one of them was cannonballs. So cannonballs, they are big and they are spherical in shape. And Robert Hooke was the one who was given. Robert Hooke was the one who was given the work on how to keep the cannonballs so that it occupies the least space, so that it occupies the least volume, and you can keep the maximum number of atoms, or you can see these spherical cannonballs. So obviously, where did he put? He would not put cannonball on cannonball. He will be putting on voids, right? Yes or no? Anna? So that he
Yes,
will
sir.
get effective packing. He will get effective packing. Now, when he arranged this whole like balls and all, and he saw that, okay, fine, I am getting some kind of cubic structures here. So he said, okay, that means if I see a crystal, if I see a naturally occurring crystal, and that is having a cubical shape or like any shape, then it must mean that if I go to a very deeper level, then also I will be getting the same kind of structure in the atomic dimensions. That is what he thought of. Okay, so he said that the crystals that we have that is naturally occurring, they owe its regular shape to the packing of spherical particles, that is ball. I mean, these are atoms only, right? These are atoms only. Packing of the spherical atoms or spherical balls that is there. So he said this from the arrangement of cannonball. Okay, from the arrangement of cannonball. Now moving on, then there we have a next scientist whose name is Steenson. You will not know him. Was working on quartz crystals. He was collecting quartz crystals and analyzing them. What he saw was, if he got some quartz crystal from island 1 and island 2, both of them, like all of them, will have some kind of 3D. They will have some 3-dimensional shape because it is a solid, and all the 3D structures, they have some face, right? So if you have some face, there will be some angle here. Now, no matter where he got the quartz crystal from, all the angles corresponding to the faces, they were all equal. They were all equal. It didn't matter where they came from. So he said that he observed this thing. All crystals have same angles between corresponding faces. Between the corresponding faces, they have same angle. Now this is now coming into some kind of conclusion when we look at Robert Hooke's thought and we see the observation of Steenson that yeah, it must be that whatever shape we are getting, it is due to the packing of the atoms that is present in the atomic dimension in the very micro picture of the crystal. Okay, so this is the inference, this was the question that we had, that if I have a macroscopic series which is regular and cubic, then can I infer and can I say that if I divide it down, getting to the atomic dimensions, will there be some cubic unit cell? So this was the question there. And if you look at, let us now look at some of the crystals. So this is one NaCl crystal. Okay, so this is one crystal. It is not that, so we like humans have not even, they have touched it, but they are not responsible for its shape. They have not cut it in this manner. Okay, so this is naturally occurring NaCl structure. Then next, this is calcite. Again, this is not cut by humans. This is naturally occurring like this. This is naturally occurring like this. Okay. Similarly, you have beryl crystals. Now, these colors are due to some kind of impurity that is present in the surrounding wherever they are found. But all of them, you can see they have they have similar type of structure that is almost hexagonal, right? Almost hexagonal. There is some wear and tear in these, but still they are all hexagonal. Now, this is amber. This is also hexagonal, as you can see. Okay, so these all are naturally occurring. So if I look at these atoms, then I can see that okay. There was one more guy, that is Reen just Hay. He was responsible for the cutting of calcite crystals, as you have seen here, this calcite crystals. And what he saw was that whatever small pieces he was getting, all the shards that he was getting, they were all rhombohedral in shape. They were all rhombohedral in shape. Also, if you look at this NaCl structure, you can see there is some breaking here and here. But even this break, whatever you are getting, that is also 90 degree. And if you break it like this, you will again get a cube. You are again going to get a cube. Similarly, here also, he just saw that all the all shards are rhombohedral. Now he was asking like how to mathematically model this. Okay, so he said that okay, fine. We have one cubic structure which can fill the space. We can have a rhombohedral that we are seeing that can fill the space. We have hexagonal that we can fill the space, right? Now he was talking about what are the distinct type of the maximum number of distinct shapes that can fill 3D space. Okay, that can fill 3D space. As we are looking at the 2D space in which we got square, we got rectangle, we got triangle, or we can also take hexagonal, right? Or we can take parallelogram, right? All of these things, they will fill the 3D space. They will fill the 3D space, and these are all distinct. These are all distinct. Now in 3D, I can't show you how it is there in 3D, but what he proved mathematically was that there are 7 distinct space-filling volume elements. There are 7 distinct space-filling volume elements, and as I see volume, that means it is filling the space 3-dimensionally. Is that clear? Yes or no? Please tell me.
Yes, sir.
Till here, everything is clear. Okay. Now moving on, what are these? Okay. Now whatever volume element I will get, that will be a 3D structure. Now a 3D structure will have A, B, C. That is the edge lengths. Okay. And there will be angles between those edges. So alpha, like this. Now this is the convention of mathematics. Now as a chemist, we are just putting forward the conventions of geometry and mathematics. The alpha angle is the angle between B and C. The beta angle is the angle between A and C, and the gamma angle is the angle between A and B. Now, if I look at here, A, B, C, alpha, beta, gamma, these are known as the 6 parameters. Now, all of these 7 distinct unit cells, they have characteristics parameters. Okay, so if you we will see what are those different units cells of crystal systems, and then we will also look at the 6 parameters that we have. Okay. So these are the 6. Okay, these are the 6. So first we have cubic one. Now in cubic, what will be the parameter? The edges will be equal. A is equal to B is equal to C. Alpha will be equal to beta, and that will be equal to gamma. Okay, and all of this will be equal to 90 degrees. Is that clear? Yes or no? Please tell me.
Yes.
Okay, moving on, we have tetragonal. Now, if I have tetragonal, now in cubic and tetragonal, what you have to do, you just take the head of the cubic structure, the ceiling of the cubic structure, and you elongate it. Okay, so increase one side. If you increase one side, what will happen? So A and B will be equal, but the C will be different, right? The C will be different. And since we have not changed the angle, alpha will be equal to beta. This will be equal to gamma, and this will be also equal to 90 degrees. We have not changed the angle of any of the sides or any of the faces. Now in tetragonal, what you have to do, you can elongate or you can stretch it from the other direction. So now what we have done, Now, all of these angles are different. Sorry, all of the edges are different. A is not equal to B. Sorry, this is B. It is not equal to C. All the edges are different. But again, we have not touched the angles. Alpha will be equal to beta, will be equal to gamma, will be equal to 90 degrees. Is that clear? Yes or no? About these three,
Yes,
cubic,
sir.
tetragonal, and orthorhombic. So you have to remember
Yes.
cubic, tetragonal, orthorhombic in one sequence. So cubic to tetragonal, elongate one side. Tetragonal to orthorhombic, you elongate another side. Okay. Now, when I look at hexagonal, then in this we have this A and B which are equal. Now, those who have done hexagonal units, they must remember it that A, B are equal, which is not equal to C because C is the height here. Now, if I look at the angles, we have alpha which is equal to beta, which is equal to 90 degree, but gamma here which is equal to 120 degree. Okay, so this is something that you have to remember. And if you do this hexagonal close packing and hexagonal unit cell, you may know these dimensions also. Wait a second. Okay. Next we have triclinic. In triclinic, you can send all of these things to clinic. That means they are all bad. That means A is not equal to B, neither it is equal to C. Alpha, it is not equal to beta, it is not equal to gamma, and this is not equal to 90 degree. Okay. Next, you will come to rhombohedral. Rhombohedral is very similar to the rhombus. In rhombus, what do we have? We have A is equal to B, and it is 3D, it will be also equal to C. And then we have alpha, which will be equal to beta, which will be equal to gamma, but this will not be equal to 90 degrees. This will not be equal to 90 degree in rhombohedral. Okay. Just remember rhombus, and then you can imagine what it is. Now, monoclinic is a bit different. This is the only one that you have to remember. In this, the sides are not equal. E is not equal to B, neither it is equal to C. But we have alpha, which is equal to gamma, that is equal to 90 degree. But beta is not equal to 90 degree. Beta is not equal to 90 degree. Okay. Please tell me, is everything clear in this whole 7 crystal systems?
Yes, sir.
Okay, no doubt.
No, sir.
Okay, Zayad बहुत late आया, क्या हुआ?
So I just came from prayer.
Sorry,
I just came from mosque.
they just came from us. अच्छा बहुत late. Why? You forgot or what?
यहाँ पे time बढ़ गया है लगता है mosque.
अच्छा. Okay. So either you can remember this in this logical manner: cubical, tetragonal, orthorhombic, hexagonal, right? Triclinic, everything is bad. Okay, alpha is not equal to beta. Okay. Sorry. This will not be equal to beta. This will not be equal to gamma. Rhombohedral will be all equal except the angle is not equal to 90 degree. In monoclinic, you'll have sides not equal, and this alpha and gamma will be 90. Beta will not be equal to 90 degree. Okay. So next we have this crystal systems, and this is how you are going to remember it. Okay, how you can remember it through a mnemonic. You can use this mnemonic, that is chrome TTH. Okay, chrome TTH. What will be with C? Which crystal system will be with C? Tell me.
Cubic.
Cubic. With R, it will be
Rhombohedral.
rhombohedral. With O, it will be what?
Orthorhombic.
Orthorhombic.
Orthorhombic, correct. With M, it will be
Monoclinic.
Monoclinic.
T will be
Tetragonal.
Triclinic.
Triclinic.
tri first. Okay, first tri, then tetra. It can be both. I mean, how would you know? Triclinic and then tetra. Okay, this is how you remember triclinic and tetragonal. H will be for hexagonal. Okay. Now, after this, what you will do? You will leave the first two and last two. Okay. Leave the first two and the last two, and then you will make how many are these? These are 1, 2, 3, 4, 5,
7.
6, and 7. Right? These are 7. You leave the first two and the last two, and then you will make a 7 like this. Can you see a 7? Tell me.
Yes, sir.
Yes.
Okay. So when you make a 7, then all the edge lengths, whatever there is, A is not equal to B, B is not equal to C, all of these are covered now. Okay. And then what you can do, you can also make the axial angles. Okay. Now, what I will do, I will stop sharing the screen now. Okay. I will stop sharing the screen because it's